All right. Hello, everyone. My name is Barna. I'm from the Craft Hub Organizer team, and let me introduce our next speaker, who is Egor Kraev from Wise. He's head of AI at Wise, and he will present about modeling and predicting customer lifetime value. Please welcome on the stage, Egor Kraev.
Hi, everybody. Thanks for having me. And without further ado, let me go into the presentation. So I will talk to you today about how to calculate the value of your customers. But first, allow me to introduce myself. I'm Egor. I head up AI and so things like machine learning and data science at Wise. And I've been doing data science before it was really called that, so applying math to questioning data since the 90s at a variety of organizations, nonprofits, investment banks, startups, and scale-ups in the US, UK, Ghana, and now in Switzerland. And I was trained in the Russian mathematical tradition and then continued my education with a master's in math at the ETH in Zurich and a PhD at the University of Maryland. And in parallel to all the interesting work in the industry, I also have some personal projects which you can find either on GitHub or a couple of them, even as papers on archive in things like molecular optimization, NLP, and so on. But even more importantly, let me tell you about Wise. So Wise's mission is money without borders. Instant, convenient, transparent, and eventually free. And we achieve this by using this kind of a website. And we offer actually three distinct products. One is the transfer service, which is quite amazingly low fees because we actually optimize for low fees rather than maximum revenue. And so that's one aspect of it. The other one, which I, as somebody who lives across multiple countries, find even more useful, is the ability to hold balances in as many currencies as you want. So with just one click, you can open yet another pot and hold Aussie dollars or Kiwis or whatever you want. And that's something I've been looking for from regular banks for a long time and didn't find it. And finally, we offer ourselves as a platform to integrate with other products. And we just went public in the summer, and we have over 10 million customers, over 3,000 employees, and are actually quite a large player scale-wise. And obviously, to make all this magic happen, we need to do quite a lot of machine learning, quite a lot of fun things. And this here is just one story, but there are many, many others going on right now in Wise, which maybe I could tell you during the questions time if you want. So how do you value a customer? Of course, the overall value of a customer to us much transcends the immediate revenue we're getting from them. But to make things precise, let's just focus on the future revenue, or if you want, net profit that we're expecting to derive from a particular customer. And that's a nice, clean concept. In fact, one could well argue that the value of a firm is nothing else than the total estimated future net revenue from all their current and future customers. So it's quite a powerful concept. But the question is, how can we actually estimate that? Well, let's start with common sense. It's amazing how far common sense can get you and how hard it is to do better with fancy models than common sense. So first of all, let's look at a particular customer. Let's look at their past frequency of transactions. Say they were on average transacting with us once a week. Let's look at the typical monetary value of past transactions. Say they were on average paying us 50 cents in fees. So we can project this into the future period we care about and then get an estimate. And so far, so simple. Except, of course, it's not. Because sadly, sometimes customers stop using us for whatever reason. And that is known in the marketing lingo as churn. And one of the difficulties in churn for companies like ours and for most internet-based companies is that customers don't tell us they're gone. They just don't come back. And so we can never know whether a customer has churned. And the only thing we can do is we say, okay, they've been transacting for a week. They've been transacting once a week on average for several months. And now we haven't seen them for a year. Chances are they're gone. So we compare the recency of the latest transaction to the typical frequency of their transactions until then. And that is the classic marketing RFM framework. Recency, frequency, monetary value. Well, okay, so far so common sense. How do we model this? Well, we need to cast it into math and then turn that math into code to actually do things with it. So there is a particularly popular family, which is called buy till you die. And what this means is that we assume that each customer behaves in a certain fashion, keeps transacting in a fashion that's kind of regular for them, typical for them, and then at some point they leave and they're gone. And in the lifetime library that I'll mention later, there are links to a lovely video by Professor Fader who describes that principle. And so this is a nice mature Python package which implements some classical models in that family. And it's really, really simple. So we want each customer has just two parameters, which is how often they transact on average and the probability after each transaction that they will desert us. And those two parameters remain constant over the whole lifetime of a customer. And for the whole customer base, we assume that the customer base is sampled from some kind of probability distribution for each of those parameters. And what all the model fits is the shape of the distribution for churn and the shape of the distribution for transaction frequency. And then we have some kind of a separate simple model for monetary value. And simple in this case means just some kind of mathematical trickery to make computing closed form expected values easy. And we're done. And I really recommend you go to the GitHub package, the GitHub page of the Lifetimes package. There are some links to the papers and to a wonderful, wonderful video by Professor Fader who explained this whole thing. So it looks simple and enticing. Let's give it a go. We start with a data set consisting of all customer transactions with a non-zero value of fees from January 1st till April 12th this year. It's about 100 days. And because we don't really want to model the rate of emergence of new customers for now, we just say everybody who has a transaction in January, that's the cohort, and we track them and we use the period until end of February as training, and then we predict March and the rest of April. And of course, there are many, many different kinds of customers in this sample. But let us focus, there are two main categories we want to distinguish. First of all, we'll have what we'll call older customers, which doesn't refer to their biological age, but just to the fact that their profile was created before the start of this sample period. And the recent customers whose profile was created in January. And there's also a mixture of two products, balance and card transactions. And in the spirit of not overcomplicating things, let's just fit the model. It's 3 lines of Python to fit the model, produce pretty plots. What does this mean? The first plot, note the log scale on the y-axis, is the distribution of transaction rate. And transaction rate, how many transactions per hour on average. And the second plot is the distribution of the dropout probability, what they call, so what we call churn. So we have a lot of people whose churn probability is around between 0 and 0.3%. And we have a small peak of people whose probability is almost 1. So customers who try us once and never come back. And then we fit the model. And the bottom left graph compares the number of customers with a certain number of transactions for the period. And in sample, of course, the fit is wonderful. All fits are wonderful in sample. If your model has enough parameters, in sample, all looks great. And then we project out of sample. And out of sample is not so good. And so what we're seeing is that the model predicts many fewer transactions across the board for all the customers than we actually observe. What's going on? Let's look at the same thing. Instead of plotting it in cross-sectional fashion, let's plot it in a time series fashion. So blue is the actual number of transactions, and orange is the model predicted one. Well, first of all, it looks like the fitter algorithm might be improved. Surely with 4 free parameters, you can do better than that. And I'll have a play with this once I get a chance. But also, the suspicion is that the problem could be due to us lumping together different kinds of customers who have different behavior patterns. So, for example, it's very reasonable to believe that card transactions will have a very, very different pattern in terms of recurrence, in terms of churn rate, all those things, from cross-currency transfers. And also that customers who are still with us after a certain period of time could have different patterns from customers who just joined and are still making up their mind about us. So let's add some granularity in here. And to begin with, let's just do a scatter plot of the quantities that I referred to earlier. So let's just have the number of transactions per customer against the average transaction size, and the average transaction size against average fee. And especially in the size versus fee plot, you see there is huge variability in there. So that you can see there's clusters in there that we need to explore. So let's start with a really simple approach and just split by older versus recent and balance versus card. And immediately you see that their distributions of churn rates are extremely different, and the distribution of transaction rates are quite different as well. So yes, there are segments. Duh. But what's even more interesting, the model performance is also very different across those segments. For the older profiles, balance prediction is actually getting to be pretty good. For all the others, for all the cards, on the contrary, it's actually the worst. And if you look at time profiles, you see the same thing. But one thing you observe here, for example, is that the churn rates are generally lower among the older profiles. And part of it is, of course, could just be survivorship bias. So people who have lower churn probabilities stick around for longer, by definition. But some of it might well be also due to the fact that people's behavior just changes. Wait, I hear you asking. But before you were talking about all kinds of other things, like maybe should we segment by frequency? Should we segment by average fees? Or, we have lots of dimensions in the data. Were those the right segments to use? Well, they were some good. They probably were not optimal. And the problem with segmentation, like I did it by hand, is it's a difficult problem, or it's a very labor-intensive problem, to be quite precise. So segmentation, you need to define the segments, split the data, look at the model on in each particular combination. And also, if you choose the segments too granular, then on each individual segment, you won't get a good quality of fit, or you won't get enough points to fit anything useful. If you choose it too coarsely, then you lump together unlike groups, and your predictive power will probably go down. So what can you do about that? I won't show it here right now, but the way I would approach this particular problem is treat it as a hyperparameter optimization method. So for example, you can say, suppose you have n dimensions, and you can split by any combination of them. This means you have n Boolean hyperparameters. Am I including this dimension in the split, for example? And then you take your favorite hyperparameter optimization algorithm. Like I've used hyperopt a lot in the past, but I hear really good things about Raytune and Flannel, and optimize for those hyperparameters. And this way, you consume compute time, but you don't use up your time, which tends to be much more expensive. And you have better things to do with your time generally. But even that might not be enough. Because first of all, customer behavior might well change over time. customers who are longer with us might have a different churn rate, not just because of survivor bias, but because their behavior is different. And also, but even more importantly, this kind of a static model doesn't capture impact of our actions. If we do a promotion, or if we write to our customers, thanking them for being wonderful customers, or to the contrary, if a customer gets stuck on an anti-money laundering check, which unfortunately happens sometimes, and those can never be quick enough, although we try to make them quicker all the time, then that could change their behavior after the fact. And if we have this kind of a static model, we can't measure that. So then we could have a separate model for that kind of impact, and we could have a separate model fit a separate time profile for churn rate changes over time, and we could have the clustering component on top, and don't forget about the monetary value on which we haven't even started. But this gets very messy, this gets very complex. And we are doing a lot of that, and it works, but it is not nice, it's not pretty. In fact, what it reminds me of is the story of epicycles. If you think back to the Greeks were trying for the first time to understand the whole world in terms of math, and their favorite kind of math was geometry. And so what they tried to do is to describe the behavior of planets in terms of geometrical figures. And the perfect geometrical figure is the circle. The planets are in the sky is perfect. Okay, there must be circles. But then you make observations, and you realize circles don't quite fit. Then you say, well, okay, maybe it's a circle, but the Earth is not in the center; it's a bit off to the side, and it still doesn't fit. Then you're saying, well, okay, let's put a circle that rolls inside another circle, and then this way this fits a little better because you have more degrees of freedom. And then maybe you add a third circle, and it kind of works. Again, if you have enough degrees of freedom, you can make anything fit anything. But it's not pretty. Well, it makes a pretty picture, as you can see here, but it's not nice to work with. And the only way people broke that was, of course, first of all, by changing their system of coordinates, by saying, well, actually, the sun is in the middle, but also by moving from a geometric approach, geometric way of looking at things, to a differential equations approach with Newton. So rather than trying to say it's an ellipse or it's a circle or something like this, then what you say is, I know the differential equations that describe the system. This means if I know which direction the things are moving at any given point in time and where they are, then I know how their speed and their position will change a little while later. And it turns out that's enough. Might turn out to be a geometrical figure, might not. But you have to abandon the whole concept of geometrical figures and move to a new way of doing things to make it work. And that's the same thing we want to try and do here. And before I describe how this works, let us summarize the limitations of the classic by-2-day approach. First of all, segmentation is a tricky manual process, and it's not easy. Secondly, for very recent customers, there is not enough data to really estimate their behavior just from their observations. And we care greatly about this. Say we have a marketing team, and that's actually exactly what one of the challenges we're facing. And then we run some kind of campaigns, and we have customers from different channels. And we want to say, what is the value of customer by channel? And we want to know it now because we need to make decisions now. And maybe this number is not the same as it was 6 months ago. But for recent customers, we haven't observed them enough. So we cannot estimate this kind of model I just discussed. Then, of course, there is the whole concept of customer behavior changing over time, and both endogenously as well as due to our actions. So what do? Well, let's be very brave and build a Bayesian neural network to address all these at once. What could possibly go wrong? Well, first we have to design it. And usually I find it useful to keep things as simple as possible And in fact, one of the reasons I love math so much is because in math, you discover that every single problem has a way that it thinks about itself. It's a natural structure. And once you understand this natural structure and work with that, then things become easy and many choices become simple. So what is the structure here? First of all, input data is a variable length sequence of past transactions per customer. And those transactions can have quite a rich structure. So we have some categorical features, some continuous features. So then you have you need to embed it into a vector from that rich structure. And then you use an RNN to turn this variable length sequence into a fixed length vector. And note that this is very, very different to a time series problem. Because in a time series problem, you have your time axis is evenly spaced. And so all the classical time series statistics assume your data is evenly spaced, and you just fit the Y and don't worry about the X or the delta X. Whereas here, this is an event sequence. So the time between events is variable and important, because that's what determines the frequency after all. So one of the things we do when preparing the data is calculate the time from the previous event and add this as one more feature. Secondly, we don't want to do customer segmentation ahead of time. We want to get it for free. And there is a way of doing this, which is you push the data through a latent space, like a variation autoencoder does. And then because you train your model for maximum explainability, then automatically you hope that the latent space will be informative. And finally, your output is just the probability distribution of what the next transaction could be. And let's look at what comes out. See, this is really super simple. And it's kind of a hybrid between a sequence to sequence and a variational autoencoder architecture. So you embed, you put it through a GRU or an LSTM, whichever is your fancy. You push it through a latent space with sampling, and then you have fully connected heads describing any kind of specific transaction features that you care about. And one added twist is, of course, churn. Because as many of you no doubt realize, we don't observe churn, as I said before. So how can you train for churn? Well, you treat it as a statistical latent variable. So what you're saying is the log likelihood. And you maximize log likelihood with two components. So we haven't seen the customer for a year, and their transaction rate is weekly. Then the probability that we haven't seen them for a year is composed of two components. One is that they're gone, and the other one is that the exponential distribution with a weekly characteristic time scale could give us a year. Obviously, when you optimize this, then you see they've churned. So you have this kind of an unobserved latent variable loss, in addition to all of the observed losses. Why is this nice? What do we hope from this? Well, first of all, like all neural networks, it allows us to add as many features in the input as we want without worrying about whether they're significant. Because we have millions of customers, as you've seen, and this is enough to avoid overfitting on dozens or even hundreds of features. And what that gives us in turn is to allow interpolation from similar customers. We don't have to observe this customer or this cohort for long enough. We can say, okay, similar customers in the previous quarter did this. Secondly, we get clustering for free. In fact, that's one of the more common applications for the variational autoencoder is unsupervised clustering, where, for example, it's been used for characterizing different types of constellations in astronomy. And because latent space embeddings are just created to allow us to predict all the different features we care about, then naturally points that are close in latent space are points that describe similar customers. So clustering is natural. And it actually goes beyond that, because now, rather than looking at just one customer or one cohort, we can look at the density in latent space of the customer density and how it evolves over time. And we haven't quite done that yet, but I'm very much looking forward to doing this in the coming months. And very importantly, the promise of this is to simultaneously train multiple heads to predict different quantities of interest. So you can have one consistent model of customer behavior for older customers, for new customers, across different products, customer types, etc. And one more reason I love Bayesian models is that uncertainty estimates come out the box. Well, so far the hopes. Does it work? The answer is almost. Like any one of you who has ever done a non-trivial project knows, if you try to do something really cool from first principles, the first version never works. Neither does the second one. But eventually, if you persevere, it generally does. So far, we are doing the silly tests, the ones that should have been decent to fail. And it can, for example, detect class. So if we train the model on synthetic data on two classes of customers, for example, one class of customers who transacts all the time, and another class who transacts infrequently. But we don't, first of all, but as an ultimate way of cheating, we tell the model so you can see the fits. On the top is the true distribution, sampled, and the very top, and the ones immediately below them are the distributions that the model outputs. And you can see them, and to the left, we actually cheat and give the model the cluster ID as an additional feature. And then, of course, it figures it out very fast. But on the right, we don't. And it still figures out that it's a bimodal distribution. And below is the clustering in latent space, so it's very nice and crisp. Now, the next step is to test the quality of our churn estimations. And that's literally something we're doing right now. And we also have several people inside the company running it against real data sets for business profiles, for personal profiles, etc. And seeing what interesting information we can squeeze out of it. Next steps. First of all, as I said, we want to train the model actual transaction data sets because, fortunately, we are not a research institution. This is there because we think it will help us understand our customers better and therefore have a business impact and serve them better. But we do also have ongoing and planned collaborations with several academic institutions to review and refine the model. And I don't want to name drop here because some of those discussions are still ongoing, but I'm very excited by this. And one particular direction, which I'm really excited to explore, is whether we can replace the uniform Gaussian prior in the classical variational autoencoder with an explicit mutual information bottleneck loss term. So let me explain to you briefly what this means. You have the latent space, and what you want is the latent space to be representative of the true essence of the stuff you care about, of the stuff you're trying to predict. And then you want to maximize two things. First of all, you want the reproduction quality, so the prediction quality to be as good as possible, obviously. Secondly, because you want to generalize, you want to just squeeze out the essential features. And one way of achieving it is just putting stupid levels of dropout and limiting the number of dimensions here, and some naive tricks like this. But really, recently, there has been wonderful research on quantifying the information theoretical quantity of mutual information. So you could actually define the mutual information penalty between the input events and the latent space. So you could force to just capture the essential stuff. And that's something we haven't done yet, but it's something I look forward to playing with in the coming future. And most importantly, for the purpose of this talk, we plan to open source the model such as it is early next year. Mainly, it's about writing the documentation and cleaning it up and making it nice and usable. So please do get in touch at Egor.Kraev@wise.com if you're interested in giving it a go. Because we, unlike certain investment banks, we believe that not every line we write is made of gold, and these kind of models are only improved through sharing. Before I go into questions, let me point out that this is just one story that is going on, one of very, very many in terms of machine learning and cool stuff. So this is just business analysis and marketing, but we also have a whole universe of things going on in crime detection, for example, and then a whole separate set of stories going on in treasury. If you thought, for example, that moving cash across the globe just in time, as cheaply as possible, is boring or simple, it's not. So we always look for smart people. So please, if you're interested in playing with cool things and doing so in the company of rather fun people, even though I say so myself, please get in touch. Are there any questions?
Great, thank you so much, Egor, for this very exciting presentation. Unfortunately, I don't see any questions on the Q&A right now, so I would like to encourage people who are still watching not to be shy, ask your questions, but I'm sure if Egor might be able to answer the questions later on as well, if you can send them to him. As Egor said, I would also encourage you to check out Wise as a career option, because I'm sure they have a lot of great things to offer. So definitely worth checking. Since I'm not seeing any questions, I'm a little uncertain. If anybody has any question, please take the time. I mean, now is the time to ask them. If you don't have any, you might be able to reach out to Egor in person, in an email, or here in Hopin as well. If Egor will stick around for a couple of minutes, Egor, will you be able to do that, or do you need to go somewhere else?
If you can point me where they are.
Yeah, so I mean, there's a people tab, and people can reach out to each other there. So you might see a red dot somewhere there, or at the top right corner, there's a little arrow, and if you get a direct message, you will be able to see that. I would say if you stick around for a couple of minutes, you might get some questions.
Absolutely.
Because I don't see them in the Q&A tab right now. But yeah, I'm sure the audience loved this really exciting presentation, and thank you very much for doing it. We are really appreciating it, and hope we will be able to see you at the next Crunch conference.
Thank you very much, and to everybody who's heard me, thanks a lot for your time. And I would really welcome any feedback. If you think I've been doing it all wrong and it could be done much better, I would love to find out how. And if you would like to collaborate on this neural event model, then I'll also be very happy to talk about that.
Great, thank you very much. I think it's time to say goodbye. So thanks again, Egor, and don't forget to reach out to Egor if you have any questions, and see you around. Bye.